Thank you for coming out for the Prosthetic Knee for Burkina Faso Symposium presentation. My name is Ashley Ha. This is Kaleb, Burch, and this is Marissa, Kuhns, and we'll be talking about the project that we've been working on for the past 2 years. So first of all, where is Burkina Faso? Burkina Faso is located in the western lobe of Africa, and the pin shows where Mahadaga is. So our partner at Mahadaga is called the Center for the Advancement of the Handicapped. And so previously, the center received knee donations from first world countries like the US. However, because of the large population of amputees, they actually exhausted the supply, and that's where we come in. And so our goal for our project is to build a low-cost, fully functional, and locally manufacturable prosthetic knee that can be integrated into the socket and the lower leg that's currently being produced and used in Mahadaga. So just to give you an overview of what to expect in our presentation today, we'll be talking about a knee and adapter design, physical testing, which includes 2D gait analysis and stance time, as well as just an overall conclusion. I'll pass it on to Kaleb to talk about a knee and adapter design.
So given the needs of our client, we went about making a design for a prosthetic knee. We started by listing our specifications. Our knee had to be under $20 by request of our partner in Mahadaga. We wanted it to be made out of steel because it's a widely available material in Burkina Faso, and it's also very strong, which will help make it last for a long period of time. We want to be able to last for about 10 years so that the patient could use it and walk on it over and over again without the knee wearing out and needing replacement. We also wanted to bear a weight of about 250 pounds to sustain the weight of an upper end patient. We also want to be able to be manufactured with simple and accessible techniques in Burkina Faso, such as welding or drilling. We also want the knee to be stable so that the patient could just stand on it without falling or walk and not fall as they're moving from place to place. Likewise, it needs to be able to connect to the prosthetic socket and prosthetic leg that they're already making in Mahadaga, and the knee needs to have a locking mechanism by request of our client. So first, I'm going to talk about the designs. This is what we came up with here, the knee and the adapter picture here. I'm going to start by talking about the knee. The knee has two main features I'm going to talk about. One is the single axis with extension assist. So if the knee operates on a single axis, which means it's just swinging freely like a hinge, but it also has this extension assist, which is a feature that's carried out by the magnet picture here. What the extension assist does is lock the knee before the patient puts their weight on it. You can see that in the graphic here. The magnet is locking the knee out in place so that it doesn't buckle as the patient steps on the leg. I'm going to go into further detail of this feature in the slide here. You can see our subject here starts with his leg standing on the prosthetic, and then he swings his natural limb forward while the magnet keeps the knee locked in place. Then he begins to swing his leg forward, take a step, and the magnet is able to disengage, which gives him enough clearance to swing his leg forward without swinging his hips out to the side. Then the extension assist feature kicks in again here, where the magnet locks the knee out in place just before he steps, and then it ensures that he's going to have stable footing and the knee will not buckle as he continues walking. The next feature I'm going to talk about is the locking mechanism. So as I said earlier, our client specifically requested this feature. This is because amputees want to be able to stand on the knee for a long period of time, while knowing that if they shift around at all, it's not going to suddenly buckle under their weight since they don't have the muscles to control it. Also, it's useful for if they're walking on very rugged terrain like you might find in Burkina. They can put the knee in this locked position where it will just stay extended and will not buckle under their weight. Next, I'm going to speak about the adapter. We made this adapter replace the standard pyramid adapters, which are pictured on the end of the screen here. These are typically used all over the world, in the US and other countries, and it's in Mahadaga they've been receiving a supply of these pyramid adapters, but they've only gotten them through donations, and they haven't reliably gotten this supply. So it's a very costly piece to use, and we wanted to offer them a more simple and affordable solution. So we came up with design that they can make there. That's the adapter picture on the center of the screen here. So there are two main features I'm going to talk about with the adapter, both of which are used to custom fit it to the particular nature of the amputee's body and their amputation. So one, you're able to rotate it, which is useful to line it up so that it's fit with the socket and the legs so that the foot and knee is straight under the thigh of the patient. And then two, we included the feature where you can translate the adapter forward and backward, which is key for ensuring stability and proper functioning of the knee. Next, I'm going to hand off the presentation back to Ashley to speak about physical testing.
So with the knee design, we wanted to make sure that our knee actually works and our patient is not in danger when they use the knee. So we actually carried out physical tests with a volunteer amputee in Mechanicsburg. So before I get into the details of our physical testing, I just want to give you an overview of a gait cycle. So a gait cycle consists of two phases: the stance phase, which is 60% of the gait cycle, and then the swing phase, which is the remaining 40%. And the gait cycle starts with a heel strike of one foot, and then ends with a heel strike of the same foot. So basically, there's 3 steps in one gait cycle. So for testing, we actually tested with 3 scenarios. One with the control knee, which is the amputee's knee, is a higher knee, a very expensive knee, and then our low-cost knee at unlocked position, and also at locked position. So we took 5 trials for each scenario, just so that we can get enough data for analysis. We also did quantitative data collection as well as qualitative data collection. So for quantitative data collection, we recorded a bunch of videos and like slow motion videos that is uploaded into the Piano Data Live analysis software to allow us to measure angles and also stance time. And then qualitative data, we interviewed our amputee just to get an understanding of how our knee compares to his control knee. So this is just a video of the amputee walking with our prosthetic knee. As you can see, he doesn't need the parallel bars, which was we were really surprised and really happy to see that. So I'll just go more into details about the 2D gait analysis that we did. So the goal for the 2D gait analysis is to compare joint angles of our prosthetic knee and see how it compares to the control knee, which is his knee, and also a healthy human limb. Like I mentioned, we recorded a bunch of slow motion videos and then captured frames of the videos that we were interested in and added angles to those pictures. So we mainly focus on 3 main angles. Firstly is the maximum knee flexion, which is at 60 degrees at mid-swing. Maximum hip extension, which is 10 to 15 degrees at heel off, before toe off, and then maximum hip extension, which is about 30 degrees at heel strike. So this table basically summarizes the results that we got, and the green column shows the results of our prosthetic knee. So mostly the angles are within range, except for instance you can see the maximum knee flexion is a little bit bigger, like larger angle, and that's because of the free swinging nature of our knee. So there's no damping features in our knee, so like the lower part of the knee is free swinging, thus the momentum causes the angle to be a little bit larger. However, all in all, we have concluded that all joint angles are within expected range, and any angles that are outside range are justified, and they don't raise any concerns to us, and no drastic changes had to be made to our design. And however, in order to optimize our knee design, we're looking into adding resistance and shock absorption, just to make sure that our knee is not too loud, because that's one of the problems that we were facing. So I'll pass it on to Marissa to talk about a stance time analysis.
Okay, I'm going to talk more about the physical testing, specifically stance time analysis. So what stance time is, it's the amount of time that passes during the stance phase of one extremity of the gait cycle. So what this means is that from